In this lesson, we're going to be learning about thermodynamics. And thermodynamics is the study of heat and its relationship to energy. Um, so when we talk about heat, and we talked about how the temperature is high and the temperature is low with two different objects, that the heat is going to flow from the high to the low object. Thermodynamics explains why. It also explains how when you have something that's hot and something that's cold, that heat is going to flow until they have the same temperature, which we call thermal equilibrium. Like when you put ice into your drink and your drink's sitting in a room, if you let it just sit there with the ice in it and the drink, it's eventually all going to come to the same temperature as the room, 68 degrees. So this would be a state of thermal equilibrium where the ice is no longer absorbing heat from the drink and the room is no longer giving heat to the drink. So everything is going to be at the same temperature. The first law of thermodynamics tells us that energy is conserved. It can be never created or destroyed, and this is the same as the conservation of energy. We're just applying it in this case to a heat system. So the energy we have before we start to transfer the heat has to be the same amount of energy we have at the end of the heat transfer. So part of the first law of thermodynamics is the adiabatic process. In the adiabatic process, we are talking about expansion and compression of gases. So in this picture here, you can see the piston is compressing the molecules down. As it compresses the molecules, they're going to turn from blue to red because the temperature is going up. The molecules have less volume. As they have less volume, their kinetic energy is going to go up, which is going to raise the internal energy of the system. If you've ever taken a tire pump to pump up the tires in your bike or something, and you pumped it a whole bunch of times, you know that the pump starts to get hot. The opposite happens when you release this valve. When you move the piston back up, then the red gives more room to move, and now there's bigger volume, so there's less energy, so the temperature goes down. So whenever you expand the gas cools down. And you may have noticed this with maybe some dust cleaner or WD-40 or spray paint. Anytime you release those gas molecules out of a canister like that, the canister always gets cold in your hand. That's because you're giving off the energy. So the internal energy in the system is going down and it makes it cold. And in some cases it can get so cold you can't even hold it. The first law of thermodynamics talks about heat exchange. The formula there, delta E equals Q plus W. Just to put that into layman's terms or everyday terms, delta E is your change in energy. And your change in energy is going to equal two things. It's going to equal the amount of heat you add and the work done on the system. So if we look up there at those molecules in the top picture, we can see them moving around. They have a molecular motion. Then when we add heat, what happens is the molecules start moving faster. So as our heat goes up here, as this Q goes up, as the Q goes up, the delta E is going to also go up. So we add heat, the change in energy goes up. If in the other direction, if we take heat out of the system, if we cool the system, the heat goes down, the change in energy goes down. So that's one of the things, how much heat we add. The other thing is how much work we do. So over here we're showing the heat transfer from work, and it's kind of the piston thing, but we add another weight onto this piston. The piston drops down. As the piston drops down, it does more work. The molecules are compressed. As the molecules are compressed, the energy level is going to go up. So a thermodynamic state is when both the heat and the work change, whichever one you're adding into the system, the change in energy is going to change as well. The second law of thermodynamics is the law of entropy, essentially. And what the second law says is that everything in a system naturally goes towards a state of disorder. Things do not get organized on their own. They always, always, always become less organized. So if you see the top picture there in A, those marbles, if they're all stacked like that, if you just give a little shake to the container, or you just let them sit there with no force on the outside of them, they're going to fall into a disordered arrangement. They're not going to naturally, if you just shake the container up and down, order themselves into that ordered array. Just like the bricks on the bottom, right? You have to do work in order to change or make things organized. Things naturally on their own become less organized. Just like your bedroom, right? Your bedroom over time is going to become less and less organized. You have to do work every single day to make your bedroom clean. Your house, if you don't do repairs on your house, if you've ever seen a dilapidated house out in the woods that's just been beaten up by nature, over time it's going to become less and less organized. You constantly have to be doing work on your house to keep it in order. And this is how every single thing in nature is. If I have a stack of coins and I drop them on the ground, if I want to get them restacked, I have to gather them all up, do the work, and stack them. They don't naturally become organized. The second law talks about why energy flows from hot to cold. It says energy never spontaneously flows from cold to hot. In a refrigerator, you have to put energy into the system to get it to keep things cold, to take the energy out of your items in the fridge. Your refrigerator is probably your most energy using device in your house. Old refrigerators in the garage suck more energy, cause you more electric bill than anything else, because it takes so much energy in order for that to cool down your food. If you were to try to cool down your house by opening up the refrigerator, you would have an opposite effect. What would happen is, if you open up the refrigerator, it would take so much energy to try to keep the refrigerator cool that the back of the refrigerator would get hotter than the actual coolness of the refrigerator when it was open. So you'd have a negative effect on the room. Another thing here with this thermodynamics is the thermal equilibrium, right? Two things are always going to come to the same temperature. I guess this is more of the first law, but like if you are out and you have a brisket, a 13, 15 pound brisket on the smoker, and you smoke that thing up to 205 degrees, and you pull it off the smoker and you want to cool it down to eat, don't put that into your refrigerator. Because what's going to happen is inside your refrigerator, everything is going to come to the same temperature. So it's going to take your refrigerator so much energy to try to cool that 200 degrees down that the 200 degrees is going to suck all the energy like out of your milk. So if as it's cooling down the brisket, the milk temperature is actually going up. So this is a good way to spoil your food, is by put something really hot into your refrigerator. So always let things cool down to pretty much room temperature. I mean, whatever, I don't want to be unsafe with whatever the food FDA says, but let it cool down before you put it in your refrigerator so you don't raise the temperature inside your fridge. Another look at entropy here, right? On the right, you can see the bricks. You have to do work to get them stacked. And on the left, if you have milk, and then there's some chocolate syrup at the bottom of the glass there, the milk and the syrup are naturally going to mix together. They're not going to unmix. So if you have this that they're already mixed together, it doesn't go in this direction. It always becomes more disorganized. The final law, and this isn't really a law, but this is the third law of thermodynamics. The entropy of a perfect crystal is zero, and the temperature of the crystal is equal to absolute zero. So remember, absolute zero is when things stop moving. So inside a crystal, crystals are ordered arrangements of atoms. We learned that when we talked about solids. So when you get it to absolute zero, you are going to have a perfect ordered arrangement inside that crystal. Every single molecule is going to be perfectly arranged. And that's an entropy of zero, when everything is in a perfect place. So that's the third law of thermodynamics.